Hello everyone, welcome back to another Stat385 video. So in this video we are going to discuss subsetting, and in the previous video we introduced generic vectors and data frames, which is a particular type of generic vector, namely lists. Lists are generic vectors, data frame is a particular type of a list, and in videos past we've discussed atomic vectors. So here we're going to consider these objects again, and then we're going to discuss different subset operations to extract different elements, and with a focus on these three operations, where this one will be understood to be preserving, so to preserve some of the structure of the the object that it is applied to, and this one will like pull out the elements themselves. This will make more sense later, and then this is just a convenient operator for named objects, and where we have various subset types. Okay, so we're going to try to go in order of objects and then go in order of subset operators and then in types. So first, let's introduce an atomic vector of the following form: 10.1 to 1.1. Okay, so the idea here is that for demonstration purposes, it makes sense to not have a one-to-one alignment between the numbers and the placement of the elements. So we're going to go in reverse order from the integer part, and have double so that it's just different than integers, because we'll use integers when we do subsetting. So first and foremost, okay, so we have a double vector, and we can pull out particular elements of it. So like this pulls the second element, third element, so forth and so on. So also we could provide a integer vector to pull out. So this is going to give a subset of indices, and then it's going to pull out the elements from this atomic vector corresponding to these indices. So the first element, the fourth element, and the seventh element. And you can see what it pulls out here. Okay. Alternatively, oops, I need to copy the whole thing. We could do all of the elements, or go in reverse order. Okay. So in each of the above, an atomic vector with the same type as x and the same length as the vector used to subset is returned, and the elements of the vector returned correspond to the elements of the original vector at the integers that were supplied. So we can use different vectors to pull out elements, or I guess this is technically a vector itself, or we can just pull out specific elements directly. Okay, likewise, we can do all but, say, the first element, or all but, say, the second element of this vector. And similarly, we could take 147, which we are combining together. In this case, remember, we're treating this as a collection of indexes for which we want the elements. So if we were to supply all negatives here, then we're pulling all but the first, fourth, and seventh, which can be more quickly written as minus and then this vector. Okay, so just to stay organized here, we have an atomic vector x, and then we have integers, which are its own atomic vector, but we're using them to subset. We're using them to come up with subsets of the elements of x. And so what we're doing with this is we're pulling out the first, fourth, and seventh elements using this single bracket notation, but noting that this subset operator preserves the atomic vector structure. Okay, similarly, and I'm going to borrow some code here, we can use a logical subset. So we can So what this is going to do is, wherever there's a true, that's going to correspond to, so there's a true in the first element of this logical vector, and that's going to be correspond to pulling out the first element of the vector. So we have trues at 1, 3, 5, 7, 9. So it's pulling out the odd elements. Okay, so one thing that we've seen before in a previous lab, or very similar idea, is I could do, say I want all of the elements x that are greater than 7. So you can see it works, but you can see what it's doing is I have the vector of 10, I have the comparison, which is a vector of 1, and so I get this nice length coercion, but it's going to turn it into a logical vector, and then I subset those elements. And so this comes in handy if you want the largest element. I mean, in this case where it's 1.1 to 10.1 reversed, you sort of know where everything's at, but like you can imagine a case where you want something where you want like large elements, or maybe even large in magnitude elements, where this is some criteria for a large element, and you want to just display what those values are. So this is very, very nice, and something that you see often is this kind of subsetting with something that is a logical vector. But when you are working with logical vectors, you oftentimes want to supply something that is the length of the object that you're studying. So again, this via length coercion will be a logical vector of the same length as x. Now you can do stuff like true, false, and it's going to recycle. There's 10 elements in x, 2 in this thing, so it just kind of recycles, and we've seen stuff like this before. However, we get into a little bit of difficulty here, for instance, because 3 doesn't divide 10, and we've seen this in the past where if we try to do this, R will complain. Over here, it will not complain, and it will just it'll recycle this 3 times, and then do partial recycling, extracting, I think, this element here, and it'll display this. These are things to just watch out for. I don't actually do this in this kind of recycling or length coercion in practice. This is kind of specifying once you get to very long vectors, you're not really going to be supplying some sort of handwritten true false statement. The most common thing that you're going to see with logical vectors for subsetting is stuff of this type of form. Okay, great. All right, so if you were to, let's copy this down. If you were to add a not applicable value here, then it will just return an NA value in the subsetting. Okay, and if you do subsetting but don't supply anything, that returns the vector itself. And subsetting a 0 element will just create an empty vector. Okay, let me just make sure. I think that should be 0. It is. Okay, and type of double. Okay, so we started with a double vector. So x0 returns a empty double vector. Okay, so that could be good for initialization purposes or something like that, but something that doesn't really happen too often. But nonetheless, something to look out for, because if you have code, this also provides an empty vector. Sometimes you can have code where you delete elements out of a vector and could end up with something empty inside of a function that you're doing, something complicated. It's something that happens, so it's something to look out for. It's not just some trivial case. Okay, so if I want to use, going back, where am I at? Logical empty 0 character. Okay, so here, say I want this or this. Nothing's going to happen because I'm not working with a named vector. Just not an element, doesn't work. So I have my double vector here, no structure. So nothing happens. Now, alternatively, if I were to create an atomic named vector, all right, let's just display it, and I do, now I'm starting to get something. So notice here with the single bracket notation, the name is preserved. So this is preserving the output is preserving the type of the object that the subsetting operator is being applied to. So that isn't always going to be the case. You can also do let's see, and you can pull multiple elements. Okay, great. Okay, so now on to, what am I doing? Atomic vectors, double bracket notation. Okay, so we just did single brackets, now we'll consider double. Okay, so we have our handy vector x. Okay, so here I'm pulling the second element out, and it's just pulling the element directly and it's throwing away all the attributes. However, here it's not easy to see what the distinction is between these two. There's no difference in this case because I'm not working with a named vector, and so they're both pulling out some atomic vector of length 1, where in this case it's just a double. So it's doing the exact same thing. Now if I go back to our named vector, now suddenly these two things will be different. So this just pulls the element itself, and this preserves the structure of the object. Namely, it's a named vector, so it returns the name. Okay. All right, so slight differences there. Likewise, if I were to do this, it's going to pull out the element itself, where with a single vector, it keeps the structure intact. Okay, and then $signs you can't apply to vectors, unfortunately, or atomic vectors. So this doesn't do anything. You just get the message here. $sign operator is invalid for atomic vectors. Okay, so now on to lists, and I'm going to copy some code overwriting my named vector. You know what? Actually, let's do this because I might want to keep that around. Okay, so what's going to happen when I do this? I'm going to take the elements of y and assign them the new name x named. All right, you can see it in the global environment. And now I'm going to take this list of different elements of different types and different lengths, and I'm going to assign it the name y. Okay, so watch the global environment changed. Okay. Oh, wow. So it calls this list data. Interesting. Okay. Perhaps we saw that before and I just didn't pick it out. Anyways. And of course, if you can use the structure command or just view it itself to see what is actually in this list. Okay. So stuff we've seen before. All right. Anyways, moving on. Okay. So with the single brackets, what this is going to pull out, this is a vector of integers from 1 to 2, very trivial, 1 and 2, and it's going to pull out the first and second objects of this, objects of this list. And I can ramp that up, do 2 to 3, do C1, 4. Great. Okay, so yeah, remember in this list of different types, the last type, the fourth object here is itself a list. So we have named element D, and then named element D has named element A and named element B, which are different types themselves. Okay. All right. So I can also display everything except for the first object in the list, just like before. All right, and you'll notice that when we're using the single bracket notation again, that the structure is being preserved, right? Like we have the list structure appearing in the print output. Okay. Right, so I can do, don't do that. True, false, true, false. Okay, great. So pull out the first and third elements using logical. Again, this recycling thing can be annoying, so be careful. Okay, so don't actually do that. I'm gonna take it off the screen. Okay, great. First and third element. This is just gonna not specify any subsets, return the whole set, the list itself. A, B, C, and D. Perfect. Okay. And Y0. So you can see here it returns a named list with no structure. So again, length 0, type of 0 list. Just let's see what happens if we pull out the metadata on this. Okay, so it does. This structure did have names, so it does recognize that if I started with this named list and substitute and basically, you know, what's the null set of this named list? It's still a named list, and that's what attributes is pulling out here. Okay, and let's see. I have. Okay, so what is Y again? A, B, C, D. 4 objects with the names A, B, C, D. So I can pull out the characters themselves, where the characters in real life would correspond, or the character vectors themselves would correspond to interesting variable names that you would know what they are in any analysis. Here it's just A and C, and I can get those objects directly. Okay, great. All right, and right, so then just going back, just a reminder, this will pull out the first object, preserving the list structure, and this pulls the object itself, not preserving the structure. So let's see, type of list, type of integer vector. Okay, so this is oftentimes you may have a list of containing, you know, numeric vectors from some output of some calculation or something, and so this is what you would actually want to pull out because you want to do a function on top of it. Okay, and that's just for ease of yeah. So that's actually doesn't actually work. Interesting. Okay. Awesome. Okay, so now where this gets going down the rabbit hole further, something, and this does come up. This isn't like purely pedantic. Okay, so we just saw that this is going to pull out the first object and just pull it out. Not treat it as type list, just pull out the actual numeric vector of, actually to be specific, of type integer. We just saw that. Now, if I want to, so this right here is an atomic vector of type integer. And so, you know, if I were to store it as something else, that's what it is. It's an atomic vector of type integer. So let's say I want to subset the elements again. Well, I can just chain these out. I can pull out the second element directly. So I can change subsetting operations. Or if I wanted to do stuff like that. In this case, it's very, very boring. Okay, fun. So I can chain these out. Okay, so now, actually, before I get ahead of myself, I can also, okay, so I'm dealing with, okay, within the double bracket notation, it's going to pull out the object itself. So I can do this for one particular name. However, if I were to do something like this, it's going to, I believe it's going to complain. Yeah. So subscript out of bounds, invalid subscript. This is a message that occurs quite often. But here, basically what's happening is if I'm pulling out objects of different types, different lengths, and I'm extracting them themselves to print out, it just isn't going to work in the same way that this does, right? Because this is actually preserving the list structure, and this is pulling out the objects themselves, and they're two objects that it's not really hard, it's not easy to reconcile how they should be combined and presented. So that's why this complains and this doesn't. So here, just go back through it slowly. Let's look at this again. So subsetting is really important. It can be very tedious. So here, I'm pulling out the first element of the list, but preserving the list structure. And now I'm calling a function on a numeric vector, so it does not work. Okay, now I'm pulling out the element itself, the integer vector of type integer, and now I can perform a function on it, a numeric function on it. Here, let's keep the order preserved. I want to subset the list and display these different objects of different types and different lengths, and so I can do it. Here, I want to do the same task, but I don't want to preserve the list structure. R doesn't know how to do this, it complains. So the type of subsetting that you're going to do depends on what your actual goals are in any particular, we'll just call it analysis. Okay. So something to be careful of. Okay, great. So, and then this $ notation is very convenient when you want to pull out elements themselves. So here we can pull out, we know that we have some list with some descriptive name, we have some variable with some descriptive name, here it's just y and a, and I want to pull out object with the name a from this named list, and I can do it directly. Let's just see, it doesn't complain. Great. So this is like a shorthand subsetting that can be incredibly useful when you're pulling out full objects from these lists. Of course, I believe you can just change subsetting too in this thing. Yeah, it works, even though it's kind of messy. Great. Awesome. All right, so now on to data frames. Okay, so recall from last time, data frames are themselves lists, but we're going to make a restriction so that the objects in the list have the same length, and the idea being that R being a language written by statisticians for statisticians, this would be some collection of measurements on individuals or subjects or whatever, and you would have the columns being the variables that you've recorded on subjects, the rows being the different subjects themselves. Okay, anyways, let's load it in. You can see the structure. Information, it's very similar to what we just did, and we can view it. Remember, this is very similar to the Y list, but here, when it's in this data frame notation, we get this nice little table to view. This comes in handy quite a bit in analysis when you're trying to get a feel for what values are. Yeah. Okay. So what happens? So keeping in mind that a data frame is a list. Some of this is going to be a little bit redundant. So here, if I use single bracket notation for subsetting, I'm going to pull out the first and second objects of this data frame. It's treated as a list, so it's in the list it like gives separate values for each object and separates them out. Here they're kind of like clumped together in the form of columns, but it's the same idea. This is going to pull out the first and second objects, or or if you like in this application in a data frame, the first and second columns, and that's exactly what it gets. And we can be more creative in what we want to actually pull out, but that's what it's doing. Similarly, we can use all but the first value, or sorry, all but the first column, first object of the list. Just 1 second here, I want to see something. So this would delete the last column. Okay, this is something that comes up quite a bit. Sometimes you're working with a data frame where you want to remove the last column, but you don't know what it is or what the dimension is, and you don't want to specify it. You do this, and yeah, works pretty well. Okay, anyways, that's going down a bit of a rabbit hole. We can subset via logicals, just like we've done before. Okay, so I have 4 columns and specifying 4 logical values, and I want, in this case, the first and third column. Okay. Great, and then if I do an empty subsetting, that's going to return the whole thing. This is very similar to a list. Okay, so one thing to keep in mind here, though, so it's preserving the data frame structure using the single square bracket notation. However, we see that there are no elements in the list, but nonetheless, it preserves the structure. There's 5 empty rows. There's 5 nothings, I guess, if you like. And then let's see what happens with this one. I bet it's going to be 0. Yes. Okay. So keep in mind that there's a similarity between length and columns. The number of objects in this data frame or in this list, they get scrunched together and form the columns of the data frame. Okay. And likewise, and this is almost very often used, is pulling out columns by their names. Okay. So something that this is used quite a bit. Using dollar sign notation on this particular list is equivalent to pulling out a variable from a data frame and then to work on. So if I have my numeric vector, then I can do mean. If I'm doing all kinds of statistical tasks, I can do stuff like this. Cool. Awesome. Okay. So let's see here. Did I do... Okay, I'm getting a little bit... Yeah, this is just... Okay, so now if I do double brackets, it's basically the same as a list. I can call out the objects by their names, $ being the shorthand for that. So what's going to happen when I do this? It complains. Subscript out of bounds. Even though they're the same length, they're different types. It doesn't really know how to do that. If I go back to single brackets and do this, what happens? It just works. Okay, cool. Okay, awesome. All right. And another particular type. Okay, so now switching gears slightly, doing something slightly different. Now we are going to look at the sort of tabular structure of a data frame, treating this as, so again, data frame is a list. So it's a collection of objects of different types where each of the objects has the same length, but it also is in this nice tabular formulation, and so we can exploit subsetting using that tabular structure. So here, I'm going to just comment this. Rows, comma, columns. Okay. So now I could do something like, I want to see all the values collected on the first and second individuals, keeping the structure intact, which is what this single bracket subsetting is going to do. And so now look, I have the information, the 4 column, or the values of the 4 variables on the first 2 subjects. You could do 1, 2, but really you're only interested in the 4th column, or the 3rd and the 4th, or stuff like this. It all sort of works. Okay, so if I'm leaving the column blank, that's empty subsetting. It's going to return all of the columns, but here I'm subsetting the rows. Similarly, if I leave, I can pull the first 2 columns, do an empty subsetting on the rows, which is going to pull all of the rows. So this would be, I want all of the values recorded for the first 2 subjects, and this is, I want all of the values in the first 2 columns, or I want all of the, what's the way to say it? I want the first 2 variables collected on all individuals. Sorry, it's not particularly challenging. I've just been rambling for a while. Okay. So we can do stuff like, I want all of the information on all subjects except for the first one. Or similarly, I want all of the information on all subjects except for the first variable collected on subjects. Man, I cannot say that. But it's, yeah, everything except for the first column. And we can mix and match. So this is exclude the first column. I don't want to look at that variable collected on the subjects, and I don't want to look at the 4th subject. And we can do that. Easy. Okay. And so we can, keep chaining this with logical subsetting, 0, so forth and so on. So what happens, just out of curiosity, if I do this? Yeah, 5 rows, and this is going to be 0 rows and 4 columns, right? Okay, interesting. Yeah, 4 columns, 0 rows. Okay. All right, so now let's do, so this is kind of tricky. So what you think it may, so we're doing the single subsetting, single bracket. So it looks like it would preserve the type, right? If I'm going to pull out the first object of this list, this is pull out first column of this data frame, or pull out first object of this list. This should preserve the list structure. So if we recall, the first element of this list is an integer vector. So it should, give it a name, preserve the name and everything. Here it doesn't. Okay, so that rule about it being structure preserving isn't quite general. Sorry. Okay, so if you want it, you can do stuff like, there's an argument. And now we can get the structure. Sometimes this is handy, sometimes it isn't. Okay. All right, so, and right, this should just pull out the first column, just like, okay, so structure preserving, not structure preserving. And when we're in this tabular viewing of subsetting, this doesn't preserve the structure either. So okay. So an interesting thing that so we've done subsetting. Now replace. Okay, so let's bring back X. Okay, so now say I want to take the first, fourth, and seventh elements of X, right? We've done this before. I could, instead of displaying them, okay, so remember, this is going to, reference X, which exists in the global environment, and it's pulling out a part of X that we want to display or use for some particular purpose. I could, however, take X, subset the values, and reassign them to something else. So right now, X147 or the elements 147 are given here. I could give them some other values. Okay. And it changed, right? Yeah. X, the first element, is now 42. Of course, it's double. The fourth element is 0.0. And the seventh element is now 8. Okay. So this is subsetting and replacing. Similarly, let's take our list Y and say that I want to, okay, so Y is a list, a named list, where the elements, there's an object given the name D, and so now I want to replace that with something else, say a numeric vector. And so it doesn't necessarily care that the existing element is a list. It's just going to replace it if we do this. Did it work? It did. We can see that D is now an integer vector. Sweet. Okay. And of course we could do stuff like get the first object, which is a numeric vector of type integer, right? We have the elements 1 to 10. Say I want elements, and I want it to be, watch the global environment. Just changed it, just reversed the first elements of the first, so reverse the first element, the first 3 integers in this integer vector, which is this first element given the name A in the list. Okay, great. So, and last but not least, we can do stuff like, so what's this going to do? Okay, so this is going to take, so we have our list, and we're going to take the third, we're going to subset out the third and fourth elements, just as refresher. We get C and D here. Okay, and then this is going to assign the value null to those third and fourth elements, null being sort of this empty set. Watch the global environment. It just gets rid of those objects directly. So if I have, say, a data frame, Z, and I have some columns in that data frame, or variables that I don't want, I could just do this. Okay. Okay, so this is actually a pretty good trick. So if I had, okay, darn it, I just got, let me go, darn it, let me go back and get that data frame. Okay. This actually comes up quite a bit. So one thing, if you're doing complicated data wrangling steps, you may oftentimes take a data frame, change it around in a way where you want to track the changes to make sure that you don't do anything irresponsibly and get rid of columns or manipulate values in ways that are that could be wrong downstream. So oftentimes it's the case to, even if you're just going to use these non-descriptive throwaway names, you may want to do something like this. So I have my data frame and I want to get rid of the first 3 columns. I could do Z2 equals Z, Z2 fa24 equals null. Okay, so now in this sequence of commands, I have Z preserved, and I have my data frame with the second columns removed. So now, in case I want to go back and keep the full and analyze or use those two columns, I haven't fully erased it from memory, whereas before I did. Okay, so sometimes this will help you stay organized if you create smaller data, or if you create different data sets as you go to preserve to track all the changes you've made. Okay, so I'm starting to ramble. This is subsetting on atomic vectors, generic vectors, data frames, or atomic vectors, lists, data frames. Keeping in mind that data frame is a type of list. Okay, so great. So yeah, so thank you for your attention. Thank you for sticking it out, and I will see you next time. All right, take care. Bye.